Okay, we are back. So, in this class, we spent in Unit 6 here with Newton's laws a little bit of time talking about connected objects. These were objects like a truck pulling a camper or two boxes that were next to each other and you're pushing on one of them and then it pushes the second. Um, when we have connected objects, remember, both objects are accelerating at the same rate. So they share an acceleration, which is a really important thing. Um, and when we talked about these connected object problems originally, we had to set them up in such a way that we had two equations because we had two objects like the mouse and the cheese on the table, or the pulley problem where we were hauling gold out from a cave. We had two objects, so we had two F equals ma equations, and using both of those equations, we could solve for things. We could solve for accelerations, we could solve for different tensions or connecting forces for these objects. That's what we did previously in this class. What we're going to look at today is we're going to have connected objects once again, but instead of our objects moving either horizontally or vertically, one of our objects, or possibly both, is going to be moving on an inclined plane. And if you don't know how to look at inclined planes or how to break up those weight components, go check out the previous video here when we look at objects on inclined planes and we learn how to break those up. So basically, the procedure that we're going to go through to solve these F equals ma problems, because remember, it's still just F equals ma. It's like everything we've been doing for months now is F equals ma. There's still going to be the same principle. We draw a picture, we set up a free body diagram, and we choose a positive and negative direction. If we can do that, we'll be set here. And the only thing that we need to remember is with our inclined plane, the weight acting down the plane, the sine of theta term, because sine of theta acts down the plane, that's actually the weight that's pulling you back down the hill, okay? So that's something to keep in mind. If we don't have friction in a problem, remember, friction is fun. If we don't have friction, then we don't actually need the normal force because there's no friction, so who cares? And the only reason this would matter is because on a plane, an inclined plane, the normal force, remember, is equal to the mg cosine theta term. But since we don't need that in a problem without friction, we could just ignore it. If we did have friction, we would need it, and we saw that in a prior example problem, and practice problem. But if we don't have it, then we don't actually need it here. Okay, so we're going to see a lot of stuff that we've already done, but just put into a more complex problem with everything kind of combined together. So let's take a look at what that will be. We have here for our example, it's a modified example. We have, and I don't know why this setup is as it is, but we have Frances. She weighs or has a mass of 53 kilograms, and that means her weight is 520 newtons. And she is sliding on a frictionless, icy ramp that's been inclined at 30 degrees. So we've got 30 degrees down here on this ramp. That is our angle right here. And she's holding on to an unstretchable rope. Remember, these are rigidly connected systems, so the rope won't stretch or it won't be a spring or anything like that. And this rope, which kind of runs up here and then kind of goes around a pulley or something, is connected to Andre, who has a mass of 72 kilograms, which gives him a weight of 710 newtons. And since they're connected together with this rigid system, they will accelerate at the same rate. So their accelerations are the same. But Andre, is moving down, and, well, he might be moving down, who knows? And Frances is moving she's either moving up the ramp or she is moving down the ramp. We don't know. We don't know who is actually pulling here. It does kind of make sense if you think about it for, a quick moment, that Andre has more mass. So he has more mass than Frances, so he should, in theory, be pulling more. And since she's on a ramp, she's not even using her entire weight to pull him. So we have a good feeling that he should be moving down here. But he's moving vertically here, okay? What we're asked to do in this problem is just figure out what is their acceleration and what is the tension in the rope. So we've got a nice picture here. We have an idea of how people should be moving, Frances moving up, Andre moving down. But let's draw ourselves a free body diagram so we could really start thinking about what's happening. So if we think about this diagram, and that'll really tell us how objects should be moving. We'll make Francis here red because he's wearing a red shirt. And if we look at the forces acting on Francis, Francis has his weight pulling down, and we know weight equals mg, but for Francis, it's just the 710 given to us in the problem. And we know since Francis is holding on to, or excuse me, Andre is holding on to the rope, there is some tension force pulling back up to him. We don't know what that tension force is. I mean, we're looking for it in part B, but we know it's there. If we take a look at Francis, she's in blue on the ramp. So here she is in blue on the ramp. She's holding onto the same rope, and that rope is pulling her with some tension going up. We don't know what it is, but we know that these tensions are the same. And we also know that she has a weight acting downward on her. So her weight is 520 newtons. But do recall, this weight isn't actually the weight that is pulling her back down the hill, or rather, not all of this weight is pulling her back down the hill. We need to figure out from this weight component how much is acting in this direction, down the plane. And we know from F equals ma that should be the sine of theta. Okay, so Francis, who is on the slope, so this is Francis right here, she's on the slope, if I messed that up with the names. We need to find her weight component acting down the plane. And remember, that is the weight parallel, which is the sine of theta term. So that's 520, because that's mg, multiplied by the sine of 30 degrees. And if you know anything about your unit circle, sine of 30 degrees is equal to 1/2. So the actual force pulling her back down the plane here will be half of 520, which should be, what is that, 260 newtons. That's how much force is actually acting down the plane here. So if we kind of think about this then, for Francis, she's got a tension pulling her up. She has 260 going down the plane. And then over here, Andre's got 710 pulling down and a tension acting up. So that right there starts to give us a really good F equals ma equation. But we need to choose what is the positive direction. Now, if you recall, on an inclined plane, we tend to tip our axis in order to think about the 260, that weight parallel pulling down and the tension pulling up the plane. But if we tilt that axis, then what's going to happen to Andre? Well, let's go back and think about the climbing problem that we did a long time ago. We had the gold climber, or the adventurer, the explorer, pulling gold up out of a pulley. And when we did that problem, we said, look, if here's a box of gold and here's a person attached to the rope, whichever direction they're moving, let's call that a positive direction. So going around the pulley was positive. So for the bucket of gold, or the bag of gold, going up was positive and down was negative. But for the person, as they're going down was positive and up was negative. So we kind of based things on the direction of motion. And if we look at our problem here, we can think of Francis. She's going to be moving up the inclined plane, and then she's going to fall off the edge and go down. Which means that if we call up the plane positive, down the plane negative, when we go around the bend for Andre, down will be positive, and up for Andre will be negative. So it's a very similar idea of what we've already done in this class. We're kind of choosing a direction to be positive, but we have a bent axis. So we're just kind of unbending it and saying, look, the direction of motion, how things are moving, will be positive. So if we go back down here to our kind of setup to help us, for Andre, down will be positive, up will be negative. For Francis, the direction of the tension will be positive, and the direction down the plane will be negative. And that makes sense because these tensions, they are equal, but they are opposite. One is positive, one is negative. That's Newton's third law right there. So with this, we can set up our two F equals ma equations. Let's set one up for Francis here, the person on the slope. So here's the Francis equation. She has a tension pulling on her in the positive direction, so tension, minus the 260 newtons, This is the weight parallel, the weight pulling her down the plane. And that's going to equal to her mass, which is 53 kilograms, multiplied by an acceleration. For Andre, a similar thing can be done. The 710 is acting down, which we've called positive. So that's 710. And then minus the tension, and that will equal his mass, which, if we go and look at that, was 72, multiplied by the acceleration. And remember, these accelerations right here, these accelerations are the same, and these tensions are the same. And that's very nice because while there's two unknowns, we have two equations, and we can solve this out. There's many ways to solve this system of equations here. Some people like to maybe move the 260 over and then substitute all of this in for t and then kind of work it out with a big substitution method. And that's totally fine if you like to do that, if that's what you see. There's nothing wrong there. What I like to do, and I was taught this by my high school physics teacher, is if I have this setup where my forces are on the left-hand side, and they are, because tension's a force, and the 260 is a force, the 710's a force, and the tension's a force. And on the right-hand side, I have masses multiplied by accelerations, and these accelerations are the same. Then what I can do is I can actually add these equations together. I can set the system to be added. And when I do that, I just take all of the values on the left here and throw them into one large equation. And that large equation would read like tension minus 260 plus, so it's tension minus 260 plus the 710 minus the tension. And as we might see there, these tensions go away. And another way that I could write it, if you're kind of just like saving yourself some time, is look, the tension and tension go away, and I'm just left with 720 and negative 260, which is all I'm left with right here. On the other side, because these are like terms, I can just add 53 and 72a together. 53 and 72 is 125a. So when I add these together, these equations, I set this system. What I eventually just have is 710 minus 260 is equal to 125a. If I do a little bit of math here, the 710 minus 260, learn to add, is 450. So I've got 450 equals 125a. This will be just under 4. So I now can just divide by 125 as we're just solving this little math problem right here. Divide by 125. And we find that our acceleration is just 3.6 meters per second squared. Okay? So there was a little bit of a system of equation that we did have to deal with right here. But we've dealt with a few of them now. This isn't the first rodeo we've been through. We see that we have another one again. That makes sense because we have two objects. And now we can go find our acceleration. If we want to find the tension for part B, all we have to do for part B in order to find a tension is take this acceleration and throw it back up into one of these two equations and solve it out. It doesn't really matter which one. Both of them have multiple terms on the left for the forces. If we throw it up top, our tension will equal 53a plus 260. I just pulled the 260 over to the other side. And then if we plug in the 3.6 for the acceleration, we have that. And now it's simply a matter of multiplying and then adding. So 53 times 3.6 gives me 190.8 plus 260. And I find that my tension in that rope is actually 450.8. And it's a force, so that needs to be in newtons. So we've done something just like that too, where we plug our accelerations back into an equation to solve for the other unknown and to solve out that system. So nothing we haven't done, but this time we had one slight change here. We had a person on an incline plane, and we had to remember that we needed to use the weight parallel to the plane to pull them back down. And that's the sine of theta component, because sine of theta acts down the plane. Tell me why. Weird tangent there. Anyways, this little example here is finished. We'll be taking a look at a practice problem next where we have a similar scenario, but sled riding once again. So until then, adios and take it easy.